Hey everyone, and welcome to another deep dive. Today we're going to tackle something that might sound a bit intimidating at first, the binomial theorem. But trust me, we're going to break it down step by step, and you'll see it's actually pretty cool and has some surprising applications.
It really is fascinating how this seemingly simple concept connects to so many different areas of math.
Right. Okay, so to start off, can we just back up for a second, define what exactly a binomial expression is? I feel like I've heard that term before, but I need a refresher.
Sure. The binomial expression is basically just any expression that has two terms that are not like terms. So you can't combine them. It's like having apples and oranges. They're distinct. So something like x plus y or 2a, 5b, 2, those would be examples of binomial expression.
Okay, that makes sense. So it's all about having two separate terms.
Yeah.
So then how does this binomial theorem thing come into play? What does it actually do?
Well, the binomial theorem gives us a powerful way to expand a binomial expression that's raised to any positive integer power. So let's say you have x plus y, and you want to raise it to the power of 5. Instead of manually multiplying x plus y by itself 5 times, which would be pretty tedious, the theorem gives us a shortcut, a formula to get that expansion directly.
So it's like a time saver for those really long expansions.
Yeah.
But I do remember those formulas looking a bit intimidating. Can we break it down a little bit? What does the actual formula look like?
Absolutely. So the binomial theorem states that x plus y raised to the power of n is equal to the sum of a series of terms. And each term has a specific form. It's NCR multiplied by x raised to the power of n multiplied by y raised to the power of r.
Okay, whoa. There's a lot to unpack there. Let's start with that NCR thing. What does that even represent?
That's called the binomial coefficient, and it's often read as n choose r. It basically tells you how many ways you can choose r objects out of a set of n objects without worrying about the order. So let's say you have 5 different colored pencils and you want to pick 2 of them. 5C2 would tell you how many unique combinations you could make.
So it's about combinations, not permutations where the order matters.
Yeah.
Got it. So then what about those exponents in the formula? Those seem pretty important too.
They are. Those exponents are key. In each term of the expansion, the powers on x and y always add up to n, which is the original power we started with. So there's a really cool pattern there.
Interesting. So there's a pattern with the exponents.
Yeah.
Anything else we should notice about this formula? Any other hidden gems?
Definitely. There's also a beautiful symmetry in the coefficients. The coefficients of the first term is the same as the last term, the second matches the second to last, and so on. It creates this really balanced equation.
Okay, I'm starting to see how this theorem goes beyond just a formula. It's about recognizing these patterns and relationships. It's pretty elegant when you think about it.
Yeah.
So can we see this in action? Can we try expanding something like 1 plus x raised to a power?
Of course. So let's take 1 plus x raised to the power of 4. Using the binomial theorem, we get the expansion, 1 plus 4x plus 6 by 2 plus 4 by 3 plus by 4. And notice how the coefficients 1, 4, 6, 4, 1 exhibit that symmetry we were just talking about.
Wow, that is pretty cool. Okay, I
Yes.
think I'm starting to get the hang of this. What about if we had something like 1x raised to a power? Does that change things up at all?
Yeah, it follows a similar pattern, but the signs alternate. So for example, 1x raised to the power of 4 expands to 1 4x plus 6 by 2, 4 by 3 plus by 4. So you see we have the same coefficients as before, but now we have alternating positive and negative signs.
So the basic structure stays the same, but those minus signs throw in a little twist.
Yeah.
So before we move on, is there anything our listener and I be wondering about at this point? Any common questions that pop up when people first encounter this theorem?
Oh, definitely. One question I get a lot is, how do you actually calculate those NCR values, especially for large numbers? It can seem a bit daunting. Well, luckily, there's this really handy visual aid that connects beautifully to the binomial theorem. It's called Pascal's triangle.
Oh yeah, Pascal's triangle. I remember that. It's
Yeah.
that triangle of numbers where you add the two numbers above to get the one below.
Right.
But how does that tie into all of this?
Each row in Pascal's triangle actually corresponds to the coefficients of a binomial expansion for a specific power. So the top row is for x plus y to the power of 0, which is just 1. The second row is for x plus y to the power of 1, giving us coefficients 1 and so on.
Wait, so if I wanted to expand x plus y to the power of 5, I could just look at the 6th row of Pascal's triangle and read off the coefficients just like that.
Exactly. And you'll notice how the triangle really nicely reflects the patterns we've been discussing. The symmetry of coefficients, the way each row connects to a specific power. It all comes together visually.
That's amazing. It's like a built-in cheat sheet for binomial expansions.
Wow.
Love it.
All right, so before we get too carried away with all these amazing patterns, let's go back to the theorem itself. Is there anything else about the formula or how to use it that our listeners might be wondering about?
Sometimes people get tripped up on how to find a specific term within a larger expansion. Like it seems like a lot of work to write out the whole thing just to find one particular term, right?
Yeah, that would be a pain. Is there a shortcut or a trick to do that?
There is. We have something called the general term formula, which is denoted as TR plus 1, and it lets us pinpoint any specific term without having to expand the entire expression.
Okay, that sounds super helpful. Can we walk through an example of how that works?
Absolutely. Let's say we want to find the coefficient of by 3 in the expansion of 2x plus 1, 7. So using the general term formula, we can directly calculate the term that contains by 3, and then just grab its coefficient. No need to expand the whole thing. So the general term formula is like a mathematical GPS. It takes us straight to the term we're looking for. I love it. I'm starting to see just how powerful this theorem can be. So before we move on to the next topic, is there anything else about the general term or finding specific terms that you think our listeners would find helpful?
One term that sometimes causes confusion is the middle term. It seems straightforward, but it can be a bit tricky depending on whether the power you're raising the binomial to is even or odd.
Oh, right. I remember learning about that a little bit. It's about finding the term with the biggest coefficient, isn't it?
Exactly. When n is even, there's only one middle term, and when n is odd, there are two middle terms. And remember Pascal's triangle? You can actually see the middle terms there. They're the ones right in the middle of the corresponding row.
Ah, that makes sense.
Yeah.
It all ties back to those patterns. So if I had x plus y raised to the 6th power, since 6 is even, I would look at the 7th row of Pascal's triangle, and the middle number would be the coefficient of my middle term.
You got it. Now let's talk about another interesting concept, the term independent of x. Sounds a bit mysterious, maybe, but it's really pretty simple.
Term independent of x. What does that even mean?
It's the term in the expansion where the x completely disappears. It's like a magic trick. It's basically the constant term where the exponent on x is 0.
Okay, I think I see what you mean. So if I expand x plus 2, 5, the term independent of x would be 25, because all the other terms would have an x in them.
Exactly. And to find this term without writing out the whole expansion, you can use that handy general term formula again. Just set the exponent of x in the formula to 0 and solve for r. That'll tell you exactly where that constant term is.
Pretty clever.
Yeah.
So we got all these tools to pinpoint specific terms. Are there any other special terms we should be aware of?
There's one more, and it can be a bit of a challenge, the numerically greatest term. This is the term in the expansion with the largest absolute value.
Oh, so now we're not just looking at the coefficient itself, but the overall value of the term.
Right.
How do we even go about finding that?
Well, it involves comparing the magnitudes of different terms, and we use a specific formula for this. You have to take into account the coefficients and the values of x and y. It might seem a little complicated at first, but it all boils down to understanding how those different parts of the binomial theorem interact.
Before we move on, any common questions about finding this numerically greatest term? Anything that tends to trip people up?
Yeah, some people get a bit intimidated by the formula, but the key is to just break it down piece by piece and really understand what each part represents. It's all about comparing the ratios of consecutive terms to see where the values start to decrease.
So finding that tipping point where the terms start getting smaller. Fascinating. It's amazing how these different concepts all connect back to the binomial theorem in some way. And we talked about Pascal's triangle as a visual aid. Are there other properties or patterns related to binomial coefficients that are good to know?
Definitely. There are some pretty cool properties that can really simplify things and show us even more about the relationships within this theorem.
Ooh. I love shortcuts and tricks. What are some of these secret weapons?
Well, for instance, did you know that the sum of all the binomial coefficients in an expansion is always equal to 2 raised to the power of n?
Wait, really? So if I expand x plus y 10 and add up all those coefficients, I'll always get 210, which is 2024, no matter what x and y are.
That's right. It's a pretty amazing property. There's another one that has to do with the sum of the coefficients at the odd positions and the sum of the coefficients at the even positions.
I have a feeling they're equal. Pascal's triangle seems to hint at that kind of symmetry.
Exactly. You're right. The sum of coefficients at odd positions is always equal to the sum of coefficients at even positions. And again, Pascal's triangle illustrates this beautifully.
It's like these patterns are built into the very foundation of math. Amazing. Are there any other properties that are particularly useful?
There's a really handy one called the recursive property. It states that NCR plus NCR1 equals n plus 1 CR. This lets us calculate binomial coefficients based on the ones that came before.
Ah, so it's like a chain reaction.
Right.
Each coefficient builds on the one before it. That could save a lot of time, especially with large numbers.
Exactly. And there are even more properties that deal with ratios of binomial coefficients, which can help simplify calculations. They may seem a bit abstract at first, but they really highlight the interconnectedness of these concepts.
It seems like mastering the binomial theorem is more than just memorizing a bunch of formulas. It's about understanding the patterns, the relationships, and knowing which tool to use in different situations. So before we move on, is there anything else about these properties or how to apply them that you think our listeners might want to know?
Yeah, it's important to remember that these properties aren't just about finding shortcuts. They actually give us a deeper understanding of combinations and patterns in math. So don't be afraid to explore them and see what connections you can find.
I'm ready for the next challenge. What else is there to discover in the world of the binomial theorem?
Wow, I feel like we've covered so much ground already. We started with the basics of binomial expressions, then explored Pascal's triangle and all those helpful properties. What else is there to uncover in this world of the binomial theorem?
Well, believe it or not, we've only just scratched the surface. We've been focusing on cases where the exponent in our binomial theorem is a positive integer, but what happens when we have negative or fractional
Oh,
exponents?
that's right. I vaguely remember those from way back when, but it's all a bit fuzzy now. Why are those negative and fractional exponents even important?
They actually open up a whole new realm of mathematical possibilities. Negative exponents represent reciprocals, so instead of multiplying a number by itself multiple times, we're essentially dividing. And fractional exponents represent roots, like square roots or cube roots.
Okay, yeah, that's starting to ring a bell.
Yeah.
But how does the binomial theorem handle these kinds of situations? Does the formula still work the same way? It does, but with a fascinating twist. When we have negative or fractional exponents, the expansion becomes an infinite series instead of a finite one.
An infinite series, whoa, that sounds a bit intimidating. Can we see an example of what that looks like?
Absolutely. Let's take the expansion of 1 plus x raised to the power of mate of 1. Applying the extended binomial theorem, we get the infinite series 1x plus by 2 by 3 plus by 4, and so on.
Interesting. So the signs keep alternating, and the exponents on x just keep increasing. It's kind of like that pattern we saw with 1x raised to a positive integer power, but now it goes on forever.
Exactly. And this infinite series holds true as long as the absolute value of x is less than 1.
Why that restriction? What happens if x is bigger than 1?
If the absolute value of x is greater than or equal to 1, the terms in the series wouldn't get smaller as we go along, and the series wouldn't converge to a meaningful value.
So it's like we need to stay within a certain boundary to make sure these infinite series behave themselves. Are there any other important things to keep in mind when working with these infinite expansions?
It's really important to understand that these infinite series are a way to approximate the original expression within that specific range of x. And depending on what we're trying to do, we might only need to consider the first few terms to get a decent approximation.
That makes sense.
Yeah.
It's like using a zoomed-in view to focus on the most important parts of the expansion. Before we wrap up, is there anything else about these infinite series or how they connect to the binomial theorem that you think our listeners might find interesting or helpful?
One common question is whether these infinite series actually have any practical uses. And the answer is a resounding yes. They pop up in calculus, probability finance, all sorts of fields where we need to model complex phenomena.
Wow, so the binomial theorem is more than just a tool for expanding expressions. It's a gateway to understanding infinite series and their applications across so many different fields. That's incredible.
Well, we've explored the power and elegance of the binomial theorem from its basic applications to these surprising connections with infinite series and beyond. I hope our listeners feel inspired to keep delving deeper into the fascinating world of mathematics. It's been a pleasure sharing these insights. Remember, this deep dive was created just for you. Keep that curiosity alive and keep exploring.
Until next time, happy exploring, everyone.